Base isolation systems, a geotechnical perspective. Welcome back to Blueprint to Reality, the channel where we uncover the science and engineering behind the world's strongest structures. Earthquakes unleash powerful forces that can shake buildings to the ground. Traditional engineering tries to fight these forces with stronger walls and stiffer frames. But what if the key isn't to resist the shaking, but to avoid it altogether? That's the idea behind base isolation systems. From a geotechnical perspective, base isolation doesn't just involve the building. It's about how the foundation, soil, and isolators interact to protect structures when the earth moves. Today, we'll explore the principles of base isolation, real-world applications, and why soil conditions make all the difference. Why base isolation matters. In seismic zones, rigid foundations transfer ground motion directly into the building, causing walls and floors to vibrate violently. Base isolation breaks this link by placing flexible bearings or sliders between the structure and its foundation. Instead of fighting the earthquake head-on, the building floats above the shaking ground, reducing damage. But here's the geotechnical challenge. The soil beneath the isolators is not uniform. Soft clay, dense sand, or bedrock all interact differently with isolation systems. A design that works in Tokyo may fail in Mexico City if soil dynamics are ignored. How base isolation systems work. Base isolators act like shock absorbers, allowing controlled movement. The goal is to extend the building's natural period of vibration, so it avoids resonance with earthquake waves. The main types of isolators include elastomeric bearings, layers of rubber and steel that deform under shaking, absorbing energy. Lead core bearings, rubber bearings with a lead plug inside, which yields under stress, providing both flexibility and damping. Sliding bearings, surfaces coated with materials like Teflon, allowing controlled horizontal sliding. Hybrid systems, combining rubber bearings with sliding mechanisms for maximum energy dissipation. Real example, the Utah State Capitol in the U.S. was retrofitted with 280 base isolators. During shaking, the entire building can move up to 60 centimeters without collapsing, proving the effectiveness of the system. Geotechnical factors that affect base isolation. From a soil mechanics perspective, the success of base isolation depends heavily on site conditions. Soil stiffness. Soft soils amplify shaking. If isolators are not tuned to this amplification, the building may still suffer damage. Settlement risks. Differential settlement beneath isolators can cause uneven displacement, damaging bearings. Liquefaction. In sandy, water-saturated soils, isolators may lose support if the ground behaves like liquid. Soil-structure interaction. The dynamic relationship between soil layers and isolation devices determines the overall system response. Case study. In Japan, base-isolated hospitals performed well during the 2011 Tohoku earthquake. But in softer soil regions, isolators had to be paired with deep foundations to prevent uneven movement. Key principles for designing base isolation foundations. 1. Soil investigation is essential. A geotechnical survey identifies stiffness, layering, and groundwater conditions. The wrong soil assumption can make an isolation system ineffective. 2. Foundation, isolator integration. Isolators must be placed on rigid foundation pads or pile caps to prevent tilting. Weak foundations can lead to isolator misalignment. 3. Period shift design. The isolators are tuned to lengthen the building's vibration period. On soft soil, the target period must account for soil amplification. For redundancy and safety, isolators are designed with safety margins. So even if some units fail, the building remains stable. Lessons from real-world earthquakes. Kobe, Japan, 1995. Base-isolated buildings had minimal damage compared to neighboring non-isolated structures. Lesson: isolation saves lives. Christchurch, New Zealand, 2011. Base-isolated bridges remain functional, while conventional ones suffer cracks. Lesson: critical infrastructure benefits most from isolation. Mexico City, 1985. Few isolated buildings existed at the time, but later research showed base isolation combined with deep piles is essential on soft clay. Lesson: soil conditions matter as much as isolators. Turkey, 2023 earthquake. Several new hospitals on isolators remain operational. Lesson: resilience isn't just about survival, but functionality after the quake. Future of base isolation from a geotechnical view. Adaptive isolation systems. Smart isolators that adjust stiffness in real time depending on soil shaking intensity. Seismic isolation for soil liquefaction zones. New designs combine piles with isolators to protect against both shaking and ground loss. Wider applications. Isolation for bridges, tunnels, and even underground metro stations. Green materials. Eco-friendly rubbers and damping materials that are both sustainable and durable. Conclusion: base isolation systems represent a shift in earthquake engineering. Instead of resisting earthquakes, we design to avoid their impact. But success depends not just on the isolators, but on the geotechnical perspective, the soil, the foundation, and the soil-structure interaction. With the right combination, cities can be built to remain safe and functional even in the strongest earthquakes. Thanks for watching Blueprint to Reality. If this video helped you understand how base isolation works from the ground up, give it a like and share it. And let me know in the comments, should I make a dedicated video on how soil liquefaction challenges base isolation systems? Don't forget to subscribe for more engineering explained, one blueprint at a time.